The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so happy to see you again. Welcome back to AO3. In the beginning of the class, I will give you a reminder about what we discussed last time. Then the main topic we are going to discuss today is about how to take good photos. Okay. All right. So let's get started. So last time we have been working together, trying to understand how to produce electromagnetic waves, which can travel to a distance which is actually very, very far away, a place which is very, very far away from the source. And what we actually figured out is that in order to do that, you have to create a kink in the electric field line such that you will propagate and produce radiation. And this is actually what we have done last time. And what we concluded is that if you want to produce electromagnetic waves, you have to introduce acceleration of that charge, such that you will be able to produce electromagnetic waves. And also we have derived, based on geometrical argument, what will be the magnitude and the direction of the radiated electric field and the magnetic field. And it's actually shown here. The radiated electric field is going to be in the opposite direction of the projection of the acceleration, A perp. Okay? The magnitude is proportional to A perp, but only evaluated at the retarded time t prime equal to t minus r over c, where r is actually the distance between the observer and the radiating charge. And the reason why we have this t prime, the retarded time, is because of the speed of propagation of information, right? So that's actually what we discussed last time. And you cannot actually instantaneously send the information about the acceleration of this charge to somewhere which is very, very far away. Therefore, the acceleration A perp is evaluated at the t prime, which is t minus r over c. The amount of time for the speed of the information traveling at the speed of light. And also the corresponding magnetic field can be also evaluated, whether through Maxwell's equation or using this formula, this D here. And finally, we will be able to evaluate what will be the pointing vector, the energy flux, directional energy flux, through exactly the same equation which we used before. That's actually what we have learned last time. And today, what we are going to do is to learn how to take good photos. Okay, so we have prepared ourselves. We know how to produce electromagnetic waves. We also know about polarization of the electromagnetic wave. And we also know how the polarizer actually works, right? So that means we will be able to make very good photos theoretically, right? So that's what we all care about. Theoretically, we can actually make very good photos. So the first thing which we would like to discuss is how to make a very good contrast when you actually take a photo of the sky, right? So as you can see, the left-hand side is a photo taken without a polarizer, and the right-hand side is a photo taken with polarizer. Okay, you can see that the contrast, or say the sky is actually darker. Therefore, you can see the cloud much more clearly. And also the same graph you can see there is a photo at the beach, and you can see exactly the same phenomenon. And now we are in the position to understand what is going on. So this is actually why we can use polarizer, okay, to make such a good photo. Okay, so So now we know what is actually happening at the sun, right? So at the sun, there are something which is oscillating, well, okay, at least some kind of emission from the sun, and those emissions are not correlated to each other, and that produce unpolarized sunlight, right? So if you look into the sun, you are looking at unpolarized light, okay? On the other hand, if you are looking at the sky, roughly like 45 or 90 degree 45 degree from the sun, okay, what is going to happen is that what you are actually seeing, all those light from the sky are actually sunlight after scattering between sunlight and the dust in the air, okay? So basically, on the sky, in our air, there are many little dust, right? And when light actually shine on this dust, they change direction. This is so-called scattering, and those light are collected by your camera, okay? The interesting thing is that, okay, if you have a molecule, which is actually here, and you have some unpolarized sunlight shining on this molecule, and that changed direction by 90 degrees, okay? What is going to happen is that since originally you have an unpolarized sunlight, therefore you have all kinds of different polarization if you look at the electromagnetic wave. However, if you only choose the light which are scattered and going toward this direction, apparently the electromagnetic wave, or the polarization, or let's say the direction of the electric field, has to be perpendicular to the direction of propagation. Therefore, what is going to happen is that only this direction, only the polarization in this direction, which is perpendicular to the direction of propagation, will survive. All the other components, like the one which is pointing upward or pointing downward, for the coming from the original sunlight, will not survive. Therefore, what is going to happen is that when you look at 45 degree, the sky 45 degrees from the sun, the sunlight is actually what kind of sunlight? Is polarized sunlight. Okay? Therefore, if you tune your filter to be aligned with the polarization, you'll be able to filter a large amount of the scattered sunlight, and that is actually how this works. And you can see that indeed the sky becomes darker after you apply this polarizer in front of your camera. Okay, so that is actually the first thing which we learned. The second thing is that, okay, we also found that the polarizer is particularly useful for the filtering of the reflected light on the window. Okay, and of course we can also use exactly the same technique to filter out the reflected light from the water, for example. And how does this work? And it turns out that this is actually much more complicated than what we thought, and we have to actually derive this, and that is actually related to the electromagnetic wave propagation inside the material, and also related to Brewster's angle, and that is actually the main topic which we are going to talk about today. Okay, so let's immediately get started. So now what we are interested in is how does this actually works, and why is this happening, and why is the reflected light become polarized? Okay, so that's the question we are trying to answer. So we have talked about electromagnetic waves in vacuum, and we also know how to generate electromagnetic wave, and now we are interested in electromagnetic wave in dielectrics. Okay, so we have talked about two kinds of materials already. The first one is a perfect conductor, and the second one, which we are going to talk about, is the dielectrics material. In case of perfect conductor, okay, it costs nothing to move all the charges inside this conductor around, and basically that will give you a zero electric field inside the conductor. Okay, and also we have unlimited supply of charges, and therefore inside this kind of perfect conductor there will be no electric field. On the other hand, if you have a dielectrics material, okay, what is going to happen is that there are a lot of charges inside the material, but all those charges are attached to specific atom or molecule. They cannot be moving freely all over the place, okay? And that is actually so-called bound to the atom or the location of the molecule. And that actually introduced a little bit of complication, okay? So this kind of material, they also respond to the external magnetic field or electric field. When, for example, in this case, I have an electron cloud, which is around the nuclei in this around the positive charge nucleus in this figure. And you can see that before we apply an external electric field, it's symmetric around 0. After we actually introduce this electric field, external electric field, there can be some kind of polarization produced because the electrons around this nucleus can be moved slightly, such that this material is actually trying to compensate a little bit the effect of the external force. Okay, so that is actually leading to a modification of the electric field. But as I mentioned, you are not going to cancel the effect, all the effect of the external field. Okay, so how do we understand this? The idea is the following. Okay, so since this system is complicated, you have free charge. Okay, it could have free charge. Okay, if we actually really kick out or add some electron into this system, it can have bound charge. Okay, and it becomes a rather complicated description. So the idea is the following: so in order to actually for our convenience to be similar to what we have been doing in vacuum case. Our goal is to define a field which is actually with the material effect subtracted. Okay? In this case, what we can do is to define a D field, okay, which is related. We hope that this is actually only related to the free charge, okay, inside the material. Okay, and then we can actually do all the tricks, which is actually similar to what we have already learned from the vacuum Maxwell equation to solve the problems inside material. Okay, so that is actually our goal. In order to do that, we have to classify the total charge, which charge density rho, into two components. The first component is the free charge, which is actually the charges which can travel freely inside the medium, okay? And the bound charge, which is actually, as I mentioned, for example, those the electron cloud and etc., where they are bound in some location, around some location in the medium, okay? So the idea is the following. So I can now define a D field, okay? This D field is so-called electric displacement field. It's defined as epsilon 0 times E field plus a P vector, which is the polarization vector. Okay, where this P vector is defined in the following way: minus divergence of the P vector is actually equal to the bound charge density, okay, which is rho B. Okay, if we have this definition and we actually continue and write down the Gauss law, and you can see that this is the Gauss law: epsilon 0 divergence of E will be equal to rho, And we also, under our classification, essentially there are two components, rho F and the rho B, the bound charge and the free charge. Okay? And according to our definition, this can be written as rho F minus del dot P vector. Okay? And now what we can do is that we can use the definition of the electric displacement field and collect all the terms except the rho F to the left-hand side. Then you will conclude that the divergence of D will be equal to rho F. Okay, so after this calculation, you can see that what we have achieved is that we have defined a field, okay, a displacement field D, which is totally related to the effect of the free charge. Okay, in this case, what we derive is actually del dot D equal to rho F. Okay, and this actually looks pretty similar to the situation in vacuum, right? Because what we actually have is epsilon 0 del dot E equal to rho. And after we actually remove the contribution of the bound charge, this becomes this expression. Okay? Any questions so far? All right, so this is actually a purely definition. And we can also do a very similar thing to the current. So the total current, J, will have the following three components. The first component is the free current, which is the current related to free charge, moving around inside this dielectrics matter. And there can be contribution from the bound current. The bound current is actually the current which is actually only moving around some specific location. And finally, the polarization contribution. So changing polarization also introduce a current, right? Because polarization is actually defined as Q dot times D, which is the distance between charges. And if I have a changing polarization, that means also there are some charges floating around, okay? And that actually gives you the third contribution, which is the JP, okay? Once we have classified the current into three pieces, and basically we can define H field, which is actually defined as B over mu 0, and the minus M, where M is a magnetic dipole moment. And the N field is actually defined as the curl of M defined as the size of, or let's say the magnitude and direction of the bound current. And once we have finished this definition, we can actually plug that into Ampere's law. Ampere's law, just a reminder, is curl of B will be equal to mu 0 times J. J is actually the total current, okay, plus a component which is actually added by Maxwell, all right? So that actually results in the electromagnetic waves, and which is epsilon 0 partial E partial T, okay? By using those definition and classification, we can immediately write down. So if we divide both sides by mu 0, basically you conclude that left-hand side is 1 over mu 0 curl of B. And right-hand side, you have the contribution of free charge current. And you have the contribution of bound current, okay? And you have the third contribution, which is related to the changing polarization. And finally, you have the term which is added by Maxwell, epsilon 0 partial E partial T, okay? By using the definition which we define here for the D displacement field, okay? And the H, which is actually related to the, which is actually defined here, okay? You can see that now we conclude that the curl of H will be equal to JF plus partial D partial T, okay? So remember why we are doing this. The reason is the following. We would like to classify the effect coming from free charge or free current inside the material by subtracting the effect from the bound current and the bound charge. Okay, so that's actually what we have been doing. Okay, then once we define new fields, which is actually shown here, D, which is the displacement field, is only related to, which is the field related to the free charge. Okay, after all those are actually just definition. And the H field, the magnetic field, which is actually only related to the displacement field and the free current, okay? We actually arrive something really, really similar to the vacuum case Maxwell equation, okay? So that is actually the excitement. And you will see that in L3, we will use immediately those conclusions, and also we will limit ourselves in the discussion of linear, homogeneous, and isotropic materials, and only work on this kind of material. And that actually will lead to a highly simplified solution for the electromagnetic field or waves inside material. Okay? Any questions so far? I hope those are just definitions. Yes? The bound current is actually inside the whole dielectrics material. But of course, you can have many, many small loops, and they will cancel, right? Because if they are looping, for example, you can have many, many bound current, which is actually fielding, which is actually surrounding the atom. But you can see that all those things, all the nearby little bound current will cancel each other. So therefore, if you do an integration, and it becomes a total bound current, which is actually happening around the surface of the dielectrics material. Yeah. So you can. So it depends on what you mean by how this bound current actually move. Okay. So you do have little ones, and if you do integral, then it becomes a surface bound current. Okay, so if we accept these two conclusions, we arrive here. Okay, basically we can immediately write down what will be the Maxwell's equation in matter. Okay, so now instead of electric field and the E and the E field and the magnetic field B field, we also have we also have, I think there's a typo there, probably. There's a typo in the lower left figure. So the lower left equation, which is unfortunately propagated to many places, should be like this. So the lower left equation should be del cross H. That will be equal to say F plus partial T. All right. So somehow this is actually propagated to many places. So basically we have Maxwell's equation in matter, which is actually really similar to what we have in the vacuum case. Okay. So very similar to the discussion we had in the vacuum case. What we actually do is to set the JF and the rho F equal to 0. Okay, if I set the JF equal to 0, the last equation will become curl of H, and that will be equal to partial D, partial T. Okay, so you can see that this is very similar to what we had before, but the problem is that we have the H field and the D field. Okay. The question is, how do we actually relate H field and the D field with the electric field? Okay. So as we mentioned before, the D field is actually defined as epsilon 0 E field plus P, which is actually the polarization of the induced polarization of the material. Okay. And in the case of very small electric field and very small magnetic field, okay? And also a linear and homogeneous isotropic material, okay? This induced polarization can be actually proportional to the size of the electric field, okay? So if this polarization is proportional to the electric field, okay, I can immediately write down that the D field is actually some kind of constant epsilon times E, okay? On the other hand, I can also discuss the H field, okay? H field is defined as 1 over mu 0, B minus M, which is the magnetic dipole moment, okay? In the case of very small magnetic field and the linear material, basically this M vector can be proportional to the B vector, okay? Therefore, I can quickly rewrite this thing since M field is also proportional to the B field in this linear material. Therefore, I can rewrite the H will be equal to B divided by mu. What is epsilon and the mu? Epsilon is the permittivity inside the material. Okay, permittivity is actually telling you the resistance. Okay, the resistance of forming electric field. Okay, in some place. Okay, so if you have a large epsilon, that means there will be large resistance. Okay, coming from the material, right? So this makes sense, right? Because that means okay, you can easily introduce or say induce a large amount of polarization in your material. Then that means this material is not happy. It's trying to cancel your electric field. Therefore, you are going. If you have a large P, that will give you a large epsilon, and therefore. That means you have a lot of resistance of forming electric field, which is still the E field here, okay, in that kind of in matter, okay. On the other hand, this mu is actually permeability of the material, which is the resistance of forming. It's related to the resistance of forming magnetic field, okay. And basically, these two quantities are actually telling you how the D field and the H field are related to the electric field and the magnetic field B. Okay. So if we assume a linear relation between D and the E, and as well as H and B, then we can actually immediately rewrite our Maxwell's equation in matter in the following way. So you can see that the resulting Maxwell's equation in matter, considering a linear material, is really remarkably similar to what we have in the vacuum case. Okay, where is the difference? Can you see that? The only difference is in the last equation, which is actually in the lower right part of the equation. Instead of mu 0, epsilon 0, you now get mu times epsilon. Okay? So what does that mean? This means that the speed of the propagation of the electromagnetic field is changed. Okay? It's now changed to instead of 1 over, in the vacuum case, you have C equal to 1 over square root of mu 0, epsilon 0. Instead of C, you are going to get C over N, which is N is the refractive index. And that is actually equal to 1 over square root of mu and epsilon. Right? It's as simple as that. So based on what we have prepared in the last few lectures, we can now immediately make sense of this equation. And now we know that almost everything is the same. What is different is that now we have a different speed of propagation, which is actually related to the refractive index we discussed last time. And now we understand what is actually this refractive index. N is actually equal to square root of mu epsilon divided by square root of mu 0 epsilon 0. Any questions? Yeah.
What are the T fields and H fields? I mean, are they just definitions?
Yes. So the D field and the H field are the field which is actually related to only the free charge, right? So you can see that now the gradients. Now the divergence of D field, okay, is actually only equal to the density of the free charge, okay? So basically, in short, the D field absorbed the effect of the bound charge into this field. And when you try to actually understand what will be the field associated or induced by the free charge, it is actually the D field, okay? But the D field is not the full story of the electric field, right? How is that related to the electric field in the exact form? This is actually defined here, okay? And from the D field, you will be able to evaluate what will be the corresponding E field. And in the linear material, there's a spatial relation between D field and the E field because the induced polarization is proportional to electric field in the linear material, which is a spatial case. And in that sense, D field is actually just is proportional to E field, and this factor is actually so-called the epsilon, which is the permittivity of the material, describing how much this how resistant how large is the resistance of forming an electric field inside the material. Okay, is that clear? Okay, good. And the H field is similar argument. All right. So now we have made sense of the electric field and magnetic field and the Maxwell's equation in matter. And in AO3, we will only discuss linear material. You can imagine that the relation between the polarization and the external electric field can be very, very complicated, right? So, for example, it depends on the how large is the wavelength of its external force, right? So if you have a very slowly varying electric field, you can imagine that you will not be able to create a polarization, which is in the electron cloud level, right? Because the variation of the electric field is too slow, right? But instead, you will be able to excite the polarization related to ions inside this material or inside the plasma, right? So on the other hand, if you have a very, very fast oscillating electric field, then you will be able to actually shift or create a polarization, which is actually related to the displacement of the electron cloud inside the atom, right? So it really depends on many, many factors. But what we have been discussing here in L3 is highly idealized linear materials and a lot of interesting things to explore in the future beyond AO3. All right, so once we have this relation, we will be able to get the Maxwell's equation in matter. And we would like to understand, just to remind you, why are we doing this? Okay, so we have a physical question. We have a question about a phenomena which we see in this slide. So when we use the polarizer, okay, very strange. It will be able to filter out the refracted light from the sun. From the sun and through when the sunlight actually hit the window and got refracted, this kind of contribution can be filtered out completely, almost completely by polarizer. So that means the refracted light is somehow also polarized. And why is that the case? Is the the question we were trying to answer here. So therefore, what I'm going to do is to, again, take a look at the boundary between two materials. The one side is actually in the air, which we call it number 1. And the other side is actually the glass, which I call it material number 2. Okay? And now I have, again, some incident plane wave, which is coming from the sun. Okay? And actually, this incident plane wave actually goes into this surface, which is the boundary between air and the glass in the discussion, which I am trying to get into. Okay, I assume that this glass is actually very, very, very wide. Okay, it's actually filled the whole universe. Therefore, this is actually just a simple plane. Okay, a boundary which actually divide our world into air and glass. Okay, we know from the discussion of previous lecture, right? So there must be a reflected light, and there must be transmission into the glass, because this is actually the general property of waves, right? So it has nothing to do with the electromagnetic wave yet, but if you have wave and you have an incident wave, you are going to have a refractive wave and a transmitted wave. Okay. We learned from the two laws of geometrical optics. We know that the incident angle theta I will be equal to the refracted angle theta R with respect to the normal direction of this surface. And we also know that the Ki, which is the wave number vector of the incident wave, Kr, which is the wave number vector, the K vector of the refractive wave, and the K vector for the transmitted wave, Kt, and this is actually theta d. These three K vectors must have a fixed relation so that the electromagnetic field, or say all those three wave equations, the sum of these three wave equations in the left-hand side world and right-hand side world, they are connected to each other. They don't break. Okay, there's no discontinuity between the sum of the left-hand side plane waves and the sum of the right-hand side plane wave. Okay, so that means it has to obey Snell's law, and there will be a fixed the size of the projection of the K vector, okay, onto the direction of this surface will be the same. Otherwise, you will have different wavelengths in the horizontal in the vertical direction. Then the electromagnetic wave will break, right? Because you can actually always change your your position when evaluating the total wave, total contribution of the incident, refracted, and transmitted waves. Okay, so once we have all those information in hand, we can actually write down the expression for the incident wave, EI, which is actually a function of R and the D. Okay. And of course, I would like to define my coordinate system first. So this is the x direction, and this is y direction. Okay, sorry, this is the z direction, actually. Okay, the x direction is going up. Y direction is actually pointing to you, and the z direction is pointing to the right-hand side of the board. And this is actually at z equal to 0, this interface between glass and the air. And now I can actually write down will be the incident wave electric field, and that is actually equal to E0I, which is a vector tell you about the polarization of the incident wave. cosine. By now, this should be looks pretty familiar to you now. This actually just ki dot r, which describes the direction of the propagation, okay, minus omega t. So this is actually describing the incident wave, which I call it EI, okay? And I will assume that since I know what will be the incident wave, the E0I is a known quantity, okay? So I say that this is actually a known quantity, all right? So now I can also do the same thing and write down what will be the refracted wave, ER as a E capital R as a function of R and T, and this will be very similarly E0R, which is actually telling you the magnitude and the polarization of the refractive wave cosine KR dot R minus omega t. All right, and finally, you have the ET, which is a function of R and T again, and this will be E0T cosine KT times R minus omega t. Okay? Of course, they will have 3 electric field. Therefore, you must have 3 what field? Magnetic field, yes. So you must have the corresponding magnetic field. Okay? So for example, BI, okay, as a function of R and the T, will be equal to 1 over V1, which is the velocity in the air. V1 is actually equal to C, right? Ki hat, the direction of the propagation cross EI. Okay? So I'm not going to write down BR and BT because this is actually a very similar expression as the corresponding associated magnetic field for the incident wave. Okay? All right? So basically, we have actually translated the physical situation into mathematics using the coordinate system which we define here. Okay? So one thing which is actually very interesting is that we have solved half of the question in the previous lecture. Right? So in the previous lecture, when we discussed 2-dimensional and 3-dimensional waves, okay, we have concluded that, okay, if you have a wave and it's continuous at the surface, z equal to 0, okay, you can immediately conclude that basically Ki dot R will be equal to Kr dot R. This will be equal to Kt dot R. Okay? This is the first thing which we actually conclude. That actually leads to what? What law? Snell's law. Yes, very good. Snell's law. Right? Okay? If this expression doesn't hold, then your left-hand side and right-hand side total electric field doesn't match at the surface of z equal to 0. Okay? The second thing which we learned is that theta I will be equal to theta R. Right? Okay? So basically, that's actually what we have learned from the previous lecture. Therefore, this matching between left-hand side electric field and right-hand side electric field become much simpler, right? Since that they are actually just some E0 times cosine some functional form shown here. Since these 3 products are identical, therefore, what is going to happen is that the location dependence and the time dependence of this relation completely cancel, right? Because you just have the individual vector E0I, E0R, E0T multiplied by a cosine function which is identical for the 3 incident, transmitted, and the refracted waves. Therefore, in the discussion of this kind of thing, you can actually ignore the location dependence and the time dependence, since they always cancel. Okay, so that's actually the pretty useful thing to have. And don't forget what is our goal, right? So our goal is to know, okay, so if I have a given incident plane wave, what will be the resulting refractive wave? What will be the resulting transmitted wave? Okay? And I would like to tell you the conclusion first. The relation between the refracted wave, transmitted wave, and the incident wave depends on the Maxwell's equation. Okay, you can see that this relation have nothing to do with Maxwell's equation so far, right? It's actually really related to the wave description we are using, and also the the matching between the left-hand side and right-hand side wave equation. Okay, so you know now we have learned this is actually only related to the genetic property of wave equation. Okay, so now we need to get the help from the Maxwell's equation in matter so that I can make sense about the relation between E0R, E0T, with respect to what is given E0I. Okay, so how do we do that? Okay, so the first thing which I would like to do is that, okay, as you see from here, I divided the whole universe into two parts. The left-hand side wall, I call it 1, is air. The right-hand side wall is glass, which is, I call it 2. Okay, therefore, I can now calculate what will be the sum of the electric field in the world number 1, okay, which is actually defined as E0I plus E0R. Okay, so here you can see that I already dropped the cosine, right, because they always cancel. Therefore, I just write down E0I and E0R without the cosine. And of course, I can also calculate what will be the total electric field in the right-hand side wall inside the glass, and that is actually equal to E0T. The question is how to relate E1 and the E2. And for that, as I mentioned, I need the help of Maxwell's equation in matter. Okay? How do we actually do that? So what we could do is that since we have Maxwell's equation, the first thing which we can do is that we can look at the perpendicular direction. The perpendicular direction means the projection of the electric field, okay, in the perpendicular direction to the surface. Okay, that's actually what I mean by perpendicular direction. Okay. So for that, I can make use of the first Maxwell's equation in matter, which is actually del dot D equal to 0. Right? We are considering the case without any free charge. Okay. So that means I have a Gauss law, which is actually D times dA. Okay, I do a surface integral, and that will be equal to 0. Okay, so this means that I can have a PO box again, like this. I arrange this PO box like this. And this is actually the surface. The size of one side perpendicular to the direction of the surface, okay, is actually called D here. And I have this box here. And the left-hand side, okay, the left-hand side D1 will be equal to epsilon 1 E perp D1 perp actually will be equal to epsilon 1 E perp 1, right? Epsilon 1 is the permittivity of the material number 1, which is actually equal to epsilon 0 actually in this case, because this is actually air, okay? And the right-hand side, you have D perp 2. This is actually equal to epsilon 2 E perp 2, okay? So now I have figured out what would be the field going to this PO box and the field going out of this PO box. Okay, what I can do now is the following. I can now shrink the size of the PO box, having D goes to 0. Okay, and it becomes very smaller, smaller, and smaller. Okay, so what is going to happen is that when this D goes to 0, this surface integral will go to what? Go to also 0, right? Okay. Therefore, I can immediately conclude that epsilon 1 E perp 1. Okay, so when I have this D goes to 0, the contribution from the side goes to 0. Okay, I know already the sum of all the contribution of this surface integral will be equal to 0, right? But I don't know what is actually the contribution from the side. But if I have the D goes to 0, then the area of the 4 sides is actually going to go to 0. Therefore, it has 0 contribution to this surface integral. Therefore, I can conclude that epsilon 1 E perp 1 will be equal to epsilon 2 E perp 2. Okay, based on this discussion. All right, any questions so far? Okay, I hope everybody is following. Now I can also use the third equation, which is actually del cross E, the fourth equation, which is actually sorry for that. I can actually use the second equation, which is the curl of E will be equal to minus partial B, partial T, right? So that means I can have integral E dot dl, and that is going to be equal to minus D dt dB dot dA. Right? All right. So if I use the third equation in Maxwell's equation, okay, basically I have an integral over a loop over some closed surface, and that would be equal to minus d dt b dot. This is actually the integral looking at the flux going through this little area. Okay. So what I can do is now I again run in the surface which connect the two worlds, and I can now define a loop which is like this, with width, this width equal to d, okay, and there can be a contribution from the magnetic field in the right-hand side integral contributing to the this equation, okay. I can immediately write down the left-hand side will be E parallel 1, right? Because right now we are actually looking at the component of the electric field parallel to the surface, right? And I can also immediately write down the right-hand side, this loop integral. You are going to have E parallel 2, okay? And now I can do exactly the same trick, right? Having this D goes to 0. Okay, the effect of this is the following. So I have this rectangular loop. And now if I have this side d goes to 0, that means you will have no area to integrate the flux for the B field, right? So therefore, if I have d goes to 0, this will be this also goes to 0, right? Therefore, I can immediately conclude that this means that E parallel 1 will have to be equal to E parallel 2, right? Based on this discussion. Okay, so this means that what we can immediately conclude that, okay, first of all, in order to figure out the relation between the incident wave, refracted wave, and transmitted wave, we need the help not only from the general property of the wave equation and also matching boundary conditions. We also need the help to provide additional boundary conditions to relate the electric field in the left-hand side and right-hand side. That is actually coming from our understanding of Maxwell's equation in matter. Okay, so you can see that the second two boundary conditions, epsilon 1 E per 1 perpendicular will be equal to epsilon 2 E2 perpendicular. And that is actually related to this surface integral of D. And the second condition, which tells us or relate the field in the parallel direction, okay, is actually also coming from Maxwell's equation, and we conclude that E parallel in the left-hand side will be equal to E parallel in the right-hand side. Okay, so we are almost there to solve the puzzle. So now what I have to do is the following. So now I would like to assume that, okay, we have some kind of polarization, okay, for the incident and the transmitted waves. Okay, so I assume that the polarization, okay, is actually the following. The polarization is actually in parallel. Okay, I assume that the polarization is in parallel to the xz plane. Okay, so that's actually my assumption. So now I introduce a new assumption, which is that the incident wave, okay, is actually having a polarization. The electric field is actually oscillating up and down, okay, in this direction, which is actually parallel to the xz plane, okay. And also I can write down the corresponding E0r vector, and finally, and this will be perpendicular to the direction of propagation. And finally, I will be able to also write down what will be the corresponding polarization for the transmitted wave, which is also, again, perpendicular to the direction of propagation. Okay? So therefore, I can now make use of the boundary condition 1 and boundary condition 2 to actually figure out what would be the relation between E0I, E0R, and E0T. The first thing which we consider is to consider the perpendicular direction. Okay? From equation number 1, I will be able to conclude that epsilon 1 minus E0I sine theta I. So basically, that is actually the contribution from the first vector E0I. Right? You can see that now I am trying to project everything to the direction perpendicular to the surface, and you can see that I have a minus sign, and that this angle is actually theta, right? So therefore, I have a therefore okay. So this angle is actually what? This angle is actually pi minus theta, right? So therefore, I have the cosine theta I, and I have this minus sign because it's pointing to the left-hand side of the board, right? Okay, so that's actually the contribution of the incident wave. And I have a second term, which is the contribution of the refractive wave, E0r sine theta I. Okay, so E0I, E0r without vector is actually just the length of the vector, okay, in my definition. Okay, and based on the first boundary condition, I have a left-hand side look like this, and the right-hand side I will have minus epsilon 2 E0t sine theta t. Right? Again, I'm looking at the projection of this E0t vector in the direction which is actually perpendicular to the surface. Okay, so that's the first expression I can get, and then from the expression number 2, okay, I can now taking the projection which is parallel to the surface, right? So now this is actually the parallel direction, and basically what I'm going to get is E0 I cosine theta I plus E0r cosine theta I. Oh, sorry, theta r. Theta r is actually theta equal to theta I, so therefore I actually replace that by theta I already. Okay, and that will be equal to E0t cosine theta t. Any questions so far? So I was pretty fast. So here I already immediately write down this is actually theta r, right? So theta r is equal to theta I, so therefore I already replaced that by theta I. Do you have any questions? So the painful period is going to end in like 3 minutes, okay? All right, so we are almost there, and look what we have been doing. We basically figure out the boundary condition from Maxwell's equation, then we are plugging in that. So we assume that the polarization is actually parallel on the plane of x and xz plane, and now we are actually just evaluating the parallel component and the perpendicular component, okay? So that's actually what we got. Okay. The goal, as a reminder, is to write E0r and E0r and E0t in terms of the norm part, which is the E0i, right? Okay. I would like to relate these three, the magnitude of these three vectors. Okay. So from equation number 1, I can actually rewrite that. Okay, basically, I can actually conclude that I can divide everything by epsilon 1 sine theta I, right? So what I'm going to get is E0I minus E0r. And this will be equal to epsilon 2 sine theta t divided by epsilon 1 sine theta I. And this is actually E0t. So basically, I'm dividing everything by minus epsilon 1 sine theta I. Then basically what you are going to get is this expression. Okay, and this actually can be related to another expression, which is actually epsilon 2 1 divided by epsilon 1 n2, right? Because I can use Snell's law, right? n1 sine theta I will be equal to n2 sine theta t, right? Therefore, I can replace this ratio of sine angle by refractive index. Everybody's following? Okay, very good. And this will be multiplied by E0t. And I can now define this. This is actually defined as theta E0t to make our life easier. The same thing can be done for the second expression. What I'm going to get is E0I minus plus E0r. Okay, basically what I'm doing is to divide everything by cosine theta I, right? So what is going to happen is that you are going to get cosine theta t divided by cosine theta I E0 t. And that is actually defined as alpha E0 E0 t, sorry. Okay, so alpha is defined as cosine theta t divided by cosine theta I. Okay, therefore, I can already immediately, based on these two expressions, to solve what would be the E0R, I can write down the solution. So basically, you can actually quickly derive what would be the E0R. And that is actually going to be my alpha minus beta divided by alpha plus beta E0I, right? And you can also solve based on these two equations what would be the E0t, and now we will conclude that this will be equal to 2 divided by alpha plus beta E0I. So this means that the refractive index will be equal to alpha minus beta. The refractive coefficient, refraction coefficient will be equal to alpha minus beta divided by alpha plus beta. And the transmission coefficient is actually 2 over alpha plus beta. Okay, so we will take maybe 3 minutes break for you to be able to ask some questions. But you can see that we have solved the relation between E0I, E0R, and the E0T. And what we have to do in the rest of the time is to enjoy what we actually already derived and what actually that means after the break. So we come back at 45. Okay, so very good. So we have survived this. And now it's time to enjoy what we have learned from this equation. All right, so welcome back, everybody. So we have actually solved what would be the refraction coefficient and the transmission coefficient tau, right? And those are the function of alpha and the beta, all right? So that's considered 3 different interesting cases. So if I have normal incidence, okay, and that means alpha will be equal to cosine theta t divided by cosine theta I. Okay, this is the definition. Okay, if I have normal incidence, that means both theta t, theta I, and the theta r will be equal to 90 degrees, right? Okay, and in this case, okay, basically you will have the same cosine theta, and cosine I. Okay, theta t and cosine theta I, and that means your alpha will be equal to 1 in this case. Okay, so in normal material, mu1 is roughly equal to mu2 and roughly equal to mu0, right? So therefore, this means that if mu1, mu2, and mu0 are very close to each other, then actually the refractive index based on that equation, which is shown there, okay, will be basically roughly equal to epsilon, square root of epsilon divided by epsilon 0. Okay, so therefore, beta will be equal to epsilon 2 divided by epsilon 1, n1 divided by n2. This is actually the definition. All right, and this will be basically equal to, since this is actually proportional to epsilon 2 divided by epsilon 1, right? And n is actually proportional to epsilon, square root of epsilon, right? Therefore, you can conclude that this actually will be equal to n2 squared divided by n1 squared, n1 divided by n2. And that will give you n2 divided by n1. You can actually cancel one of the n2 and one of the n1. Okay? So beta will be equal to n2 divided by n1. And therefore, you can conclude that R will be a function just related to the refractive index. So which means that you are going to get N1 minus N2 divided by N1 plus N2. Okay, which means that the amount of refracted light is related to the difference in the refractive index. Then the amount of the transmitted light will be equal to N1 divided by N1 plus N2. Okay, so what does that mean? This means that if you have some material which is actually like diamond, okay, diamond have N2 equal to something like 2.6. That means a lot of light will get refracted when you have no more incidence, even if you have no more incidence. Okay, so that's actually why the diamonds are so beautiful, right? It's because a lot of light is pretty bright, and a lot of things are actually refracted. The transmitted fraction is actually pretty small. I can also assume that there can be a grazing incidence. Okay, that happens. This means that I am going to have theta I. This theta I, this theta I should be here. Okay, this theta I is actually going to be roughly 90 degrees. Okay, in the case of no more incidence, theta I should be equal to 0. Okay, maybe I misspoke in the beginning. Okay, so what does that mean? This means that alpha will go to infinity because the theta I is going to 90 degrees. Okay, therefore you have R roughly equal to 1 because R is actually alpha minus beta divided by alpha plus beta, right? If alpha goes to infinity, then R will goes to 1, right? And the tau will be actually goes to roughly goes to 0. All right, so that means if you have a glazing incidence, then basically most of the light are refracted. Okay, so that's actually why when we see when we see for example, a refracted light from the sun, which is actually on the road. Okay, we see that a lot of light are refracted. When we see a lake, which is actually very far away from me, and there's sun in front of it, you see a huge amount of light got refracted and go into your eye. It looks really, really bright. Okay. So finally, there is a very interesting angle, which is actually considering a situation when alpha is equal to beta. Okay, there is a very interesting angle, theta b. If we choose this theta b such that alpha is equal to beta, what is going to happen? Somebody can tell me. If I make exactly, right? So if you choose an angle such that alpha is equal to beta, then R will be equal to 0. There will be no refraction, and everything will go through the material. Okay? So that is actually so-called Brewster's angle. Okay? And this happens when theta b, which is actually theta b is actually the incident angle, okay, plus theta d is equal to pi over 2. Okay, there is a proof of this Brewster's angle in the lecture note, but we are kind of running out of time. But the conclusion is that you will need to have theta b, which is actually equal to theta I, the incident angle, plus the transmission light angle, theta d. If that is actually equal to 90 degrees, then you can make alpha equal to 0. And what is going to happen is that there will be no refracted light. Okay, so when this happens, when the refracted light and the transmitted light have an angle of 90 degrees, then the amplitude goes to 0. This is actually a very interesting property, and it only works for electromagnetic wave because this is actually coming from really the effect of Maxwell's equation. Okay, so now what I'm going to say is that basically, if you look at this demonstration, so if you have an incident light, okay, and the transmitted light. Originally, the incident light is unpolarized, so you can have all kinds of different polarization. So we can decompose polarization into a component which is actually pointing to you, which is the dot, and the component which is actually parallel to my slide, which is actually what we have been working on, okay, the situation. So what is going to happen is that the component which is pointing you is actually never gets suppressed because there will be no perpendicular component. So therefore, even if you are at Brewster's angle, okay, it can actually get refracted. On the other hand, all the components which is actually having polarization parallel to this slide is eliminated because of this relation. Okay, so that means the refracted light will be highly polarized. Okay, do you believe me? Maybe not. We can do an experiment and really show you that's the case. Okay, so we are almost there. So now I need to turn off the light and hide the image. And you can see that there is a setup here which I produce unpolarized light, and there's a glass here which actually reflect the unpolarized light. Okay, so now you can see that if I have some random angle and I have a polarizer here, I hope you can see it. You can see that the polarizer cannot eliminate all the light, right? So basically, no matter what kind of direction, I will not be able to eliminate all the incident, the refracted light. This means that there's some mixture of all kinds of different polarization. But now, if I change the direction to Brewster's angle, it's roughly here. So you can see that now, indeed, I can actually eliminate all the contribution of the refracted light because the refracted light is highly polarized. As you can see from the slide, all the component which is actually parallel to the slides is actually eliminated due to Brewster's angle, and that produces you a polarized light, and that can be filtered out by the polarizer. Okay, so coming back to the question which we had before, so why can we take such a good photo? That is because of Brewster's angle. So once the sunlight got refracted by the window, it becomes linearly polarized, and therefore you can actually filter out the majority of the contribution by using polarization filter. Okay, thank you very much, and I hope you enjoyed the lecture today, and hope this will improve your technique or skill for taking good photos. Okay, if you have any questions, please let me know.
Hello, everybody. Today I'm going to show you a demonstration of Brewster's angle. So during the class, we were discussing about how to make very good photos, how to use polarizer to filter out the refracted light from the sun. Usually when you actually take a photo of water or a car, there are refracted light from the sun on the window or from the on the water, and then you can actually use polarizer to filter them out. And that has to do with the property of the electromagnetic wave and the Brewster's angle. So here I have an experimental setup here, which consists of 3 components. The first component is a unpolarized light source. Okay, and it emit unpolarized light, and those light got refracted by glass here, and the refracted light will actually be shown on the screen as a spot there. Okay, so at first, if I have my glass, which is actually the position of the glass is in a way such that it's actually not on Brewster's angle. And now I can actually check if this light is actually polarized by using a polarizer here. And if I put this polarizer between the screen and the glass, you can see that as a function of the angle, which I'm rotating this polarizer, you can see that no angle can actually completely eliminate or the refracted light. Okay, so that means the refracted light is actually not perfectly polarized, but on the other hand, you can also see that in some angle, you can actually significantly lower the intensity, and that is actually also pretty good for photo taking, because that means all the refracted light, although now the angle is actually not at the Brewster angle, you still have the refracted light slightly polarized. Okay, so that actually your polarizer in front of your camera will still do some work. Now what I'm going to do is to change the angle so that it match with the Brewster's angle. So now you can see that if I insert a polarizer between the glass and the screen, you can see that at some angle, for example now, we can actually filter out or completely eliminate the spot on the screen. So that means at Brewster's angle, okay, basically the refracted light is actually completely polarized, as we actually predicted from the lecture. And the reason is the following: there's only one direction of the polarized light from the unpolarized source can get refracted due to the boundary condition of the electromagnetic wave, and therefore we see this very unique phenomena which we can only see in electromagnetic waves.